Hi, my name is Arash Pouryazdan, and today I'm delighted to present a work that my colleagues and I have been researching on non-contact measurements of DC potentials with application in static charge imaging. So without any further ado, I'm going to present the slides to you. So a typical way of measuring DC voltages is to use resistive contacts. A cheap way of doing it is to use multimeters or SMUs. But this is not always possible. So sometimes safety requirements do not allow to get close to the source on the test. Sometimes the terminals of the source are encapsulated, and sometimes making the resistive touch creates artifacts such as galvanic reactions or causes mechanical damage to the device on the test. So if you have a silicon die or thin film devices, transistors, making resistive contacts with probes may damage the surface. And an ideal application for this type of work would be battery characterizations. I must say there are other techniques such as field mills and Buckle effect sensors, but they are mostly designed to measure very high voltages, and also they suffer from being able to only do a single-ended measurement, whereas the technique we're providing today is a two-point true potential measurement. The heart of the technology we're presenting today, or the technique we're presenting today, is a ultra-sensitive voltage amplifier known as EPS, patented at the University of Sussex and has also been commercialized. Is classified as a type of capacitive sensor. Its novelty lies in its tera-ohm input resistance and femtofarad range of input capacitance, and is also DC stable. Various AC measurements has been done with this type of technology in the past and published in both macro and micro scale. The image you see from the banknote below, it's a dielectric characterization of ink inside this banknote. We also presented a method for measuring AC voltages from distances of up to 600 millimeter away using a commercial version of this EPS sensor in 2019 IEEE conference. But here we're going to talk about doing a DC measurement. The principle of operation of this technique is very intuitive. So we have a conductive sensing probe. We move this probe, in this case is a coaxial cable, within a gradient of a static or DC electric field. There is a capacitance between the sensing probe and the source on the test, and this capacitance will subsequently be charged up. And the voltage that is created across this capacitor will be measured using the EPS sensor. The movement of the probe will cause a transient signal or an AC signal, and that's what is being measured. By combining the output of the sensor with the probe position and the velocity, we are able to calculate the potential difference of the source under test. In this case, the battery terminals. The battery terminals can be both encapsulated or insulated or exposed. We used a bespoke EPS sensor. There's a computer-controlled XYZ stage to move the sensor and its sensing probe over the sample. We used some very simple analog signal processing techniques, like a first-order high-pass filter, a first-order low-pass filter, some gain, and we digitized the signal using standard National Instrument USB devices. Here we show an example of the non-contact DC measurements. We use the PCB sample as the source on the test. The sensor to sample separation in this case was 0.4 millimeter. We moved the sensing probe at a constant velocity of 6 millimeters. And we done the measurement for both exposed and insulated terminals. So the terminals were insulated using Kapton tape in this area, and we had the exposed copper area in this case. We varied the source voltage from 0 to 5 volt. And as you can see in the graph on the right-hand side, the sensor output is a function of two different parameters, the time and distance, which are both interrelated depending on the velocity. We also verified that this technique works using a floating voltage source, i.e. a battery, to ensure that there is no current path between our power supply, that is our source on the test, to the sensor and the rest of the electronics in the computer. We've come up with a simple mathematical model for characterizing and calculating the output voltage or the voltage of the source based on the output voltage. The coupling capacitance here refers to the capacitance between the source and the probe and is governed by its dimensions and its separation to the source. Rin represents the input resistance of the EPS sensor, and Cin represents the capacitance of the sensing probe itself and the EPS sensor. The K factor is a calibration factor and is a combination of the gain used for the EPS sensor and the Cin that can be varied based on the probe used. By simply integrating the output of the sensor with respect to time, we are able to calculate the voltage of the source on the test. So we've done a measurement once for exposed conductive terminals. We repeated this measurement 5 times to calculate the errors, and we varied the voltage of the source on the test from 0 volt to 5 volt, and achieved a 80 millivolt minimum detection with a plus minus 1.5 volt error. In this way, we basically took the peak value of the transient signal. And we also used the integral method to extract the voltage of the source on the test. And then we managed to achieve a better minimum detection voltage of 30 millivolts, and the error was also reduced to 1.2%. And what's interesting is that the source voltage and the sensor output have an extremely linear relationship, which is very desirable for any sensor technology. We repeated the same measurement for insulated terminals, and the insulation used in this case was Kapton. As you can see, in comparison to the previous measurement, the error has increased to plus minus 9%, and for the peak extraction method, and for the integral method, the error was even higher to plus minus 14%. This can be attributed to the accumulation of the surface charges on the insulator used. As you can see, the sensor output voltage has also been reduced in comparison to the exposed terminal. This can be attributed to the field lines being confined within the dielectric, so the insulator will have a higher dielectric constant than the air in case of the exposed terminals. We also investigated the scanning speed and sample to probe separation. As you expect, when the speed is increased, the sensor output will be higher, and also the frequency of the transient signal will be higher. So here we've gone from 12 millimeters per second all the way down to 0.75 millimeters per second. And we also investigated the sample to probe separation. As expected, as the separation increases, the amplitude of the measured signal decreases, because simply the coupling between the sensor and the source on the test has been reduced. One of the interesting applications for this method, as well as measuring DC voltages of encapsulated variable devices and flexible electronics, is to do a static, electrostatic distribution charge imaging of insulators. So here we are looking at a fingerprint that has been deposited on an insulating film by contact electrification. So contact electrification refers to touching of two dissimilar material. Here we used a slightly smaller sensor with a spatial resolution of 36 micrometer. This technique is sufficient for identification purposes, and because this charge decays slowly over time, and we're talking about weeks, we are able to provide a timeline of deposition of this fingerprint on the surface. So here we are looking at the electrostatic charge distribution. Here's a line profile of one of the lines of the fingerprint, and here's an optical image of the very same fingerprint. So in future, we would like to implement this technique specifically to diagnose electric vehicle battery cells. They are encapsulated. So while they are in production facilities, or while they are mounted inside the vehicle, it would be beneficial to be able to measure or diagnose individual cells by scanning them without needing to open and access the terminals and probe them resistively. We would also like to investigate the influence of the surface charges on different insulating materials. Further, we also are working on a new method to completely eliminate the need for mechanical movement of the sensing probe, which has been fairly successful so far. And we are looking to explore other electrostatic charge imaging applications other than the forensic application that I just presented to you in the last slide. I hope you enjoyed this. I'm happy to answer any of your questions. Thank you very much.